All right, and then our last speaker before coffee is Isabel, and they're going to tell us about the road to detecting spectral binaries with data-driven models.
Okay, great. Can people hear me okay? Great. Yeah, thanks for having me today. My name's Isabel Angelo. I'm a sixth-year grad student at UCLA, and I'm going to be telling you about a project that I've been working on with my advisor, Eric Pettigura, and also Megan Bedell at Flatiron Institute. So I probably don't need to tell a lot of people in this room this, but for planets that are detected with photometry, like Kepler and TESS planets, they are oftentimes mistaken for binaries are oftentimes mistaken for single stars in these planet census. And that's because the large pixel size of these photometric missions like Kepler and TESS that can often not resolve two stars in a single pixel. And so as a result, we've got a lot of planet hosts that are probably classified as single stars that might actually be unresolved binaries. And this has a lot of negative effects on the population and our knowledge of it. So you can get things like underestimated planet radii from diluted transits. You can also get errors in planet radii at the population level, which leads to uncertainties in things like the radius gap that a lot of people have talked about. And then more generally, it also just leaves open a lot of questions about whether and how planets form in binaries. If we don't know which of our planet hosts are single stars and which are binaries, we can't answer questions about the types of environments that planets form in or their dynamical environments. So there are a lot of problems that come from these larger pixel sizes. And there are also a lot of people who have been trying to tackle these problems, namely by following up Kepler and TESS planets and their planet hosts to check for whether or not they're binaries. And so you need to use a lot of different detection methods in order to look for specific types of binaries. So on the wide binary end, you can follow them up with really high resolution imaging or adaptive optics. Adam did a paper about this in 2016. If you've got really close binaries, these will appear as what we call SB2s. So you've got a large RV offset between the primary and the secondary star. It kind of looks like two spectra on top of each other, and you can detect them this way. But there are binaries that are kind of in the 10 to a couple hundred AU separation regime where it's really hard to find them with these two methods. I'm going to be calling these spectral binaries, and I'll talk about the work that I've been doing to try to detect binaries in this gap. This gap is really important because it encapsulates that 40 AU peak where we expect actually most binaries to reside based on field stars. So we really want to be able to detect binaries in this gap here. So what is a spectral binary? I'll start by defining that. When we have SB2s, it's kind of clearly a sum of two spectra with an RV offset. If you've got a binary that's in a wider orbit, you might not have an RV offset, but instead you would have a sum of two stars that have no RV offset, or in other words, overlapping spectral features. And so to your eye, that might look like that black unresolved binary in the top panel, but it can still show up in the spectrum, essentially manifesting as deviations from single star behavior. So you can see here that the binary does look different from the best fit single star in the bottom panel. And we can detect these deviations from single star behavior as a spectral binary, but the key here is that you need really, really accurate spectral models to be able to do this. So this is what we worked on next, is essentially training these specific types of spectral models called data-driven models that have kind of emerged in the past 10 years. So these models are really helpful for our purposes because they sidestep a lot of systematic uncertainties that physical models might have, maybe in their radiative transfer calculations or line lists. And instead what they do is you feed them a bunch of real data. So you give them spectra, and then you give them properties of those spectra that you know exist. Things like the temperature, surface gravity, and abundances of the star. And then it undergoes a training step where the model essentially learns how the flux depends on these stellar properties. And what you get out of it is a spectral emulator that can essentially predict the flux for a given set of spectral star properties. And it can also determine star properties based on some flux that it's been given. So we trained for this project, I'm using high-res spectra. This is because a lot of planets, as people have talked about, their hosts have published high-res spectra already. So we're looking at planet hosts that have high-res spectra, and I trained two different types of data-driven models, the Cannon and the Pane. They are pretty similar in their nature, but the Cannon uses linear regression and the Pane uses a neural network, so they're kind of two different steps towards the same goal of predicting flux as a function of these star properties. And now I'll talk about a little detour that was kind of interesting that we went down when we were training these data-driven models, which is that we came up with a sort of new and different way to treat the continuum of stellar spectra. So a lot of the spectra from high-res come out deblazed, which means that their instrumental blaze function has been removed, and for a lot of purposes, this is like perfectly fine. The continuum is well treated. But for these data-driven models, you need the continuum to be very, very well removed. Otherwise, it's going to mess up the training step of your model. And so you can see here on the left, we started with these deblazed spectra from high-res, and while they look continuum normalized, I would point to like this part between the two deep features on the right. You can see that they deviate from the line of unity to different degrees for each of these spectra. This is basically just something that happens because of the instrumentals. It's not due to the physical properties of the star. And so this was limiting our model precision. We were only able to infer stellar temperatures to about 100 Kelvin, and we wanted to go further than that. So we developed this new approach to continuum normalization called wavelet-based filtering that I'll describe in the next slide. But it produces spectra that when we trained our model, we were able to get temperatures precise to about 60 Kelvin now, so there was almost a factor of 2 improvement from this type of filtering. You can see here that the spectra don't necessarily look continuum normalized in the classical sense, but the key thing to note about them is that when they deviate from this line, they deviate in the same way. So it's no longer an instrumental thing. It's happening uniformly to all the stars. It's not affecting our model anymore. So this is something that I think might work for people who are training data-driven models and don't want to go through kind of annoying continuum normalization, which I found to be pretty painful. And this is how it works. So it's similar to a Fourier transform in its first step, where you do a wavelet decomposition, but instead of decomposing the signal into just sines and cosines, which are only characterized by frequency, we decompose the signal into these wavelets, which I show in the upper right-hand corner. And these are characterized by their frequency and also their location on the x-axis, which in our case is a wavelength because we're looking at spectra. And so when you do this wavelet transform, kind of like a Fourier transform, you're getting a power spectrum out of it, but you actually get a number of different power spectra, each corresponding to different frequencies of different wavelets. And then the x-axis will be the x location or wavelength of that power spectrum. So you can see the decomposed spectrum here in the middle, and it's going from lowest frequency components of the signal to highest frequency components of the signal from the top to the bottom. So we'd expect the bottom to contain a lot of the information from noise, the middle levels to contain a lot of information from the spectral features themselves, and then the upper level to contain information from the continuum because that's lowest frequency behavior in the spectrum. So we essentially just decompose the signal, remove that continuum level from it, and then inverse wavelet transform to get back a wavelet filtered signal that essentially doesn't have these continuum variations in it anymore. So this ended up really improving our model performance, and that's kind of what I wanted to show you here in this plot. So the way that we check whether or not our model is performing well is we try to determine star properties with it, and we compare them to these sort of ground truth properties. In this case, the star properties reported by the California Kepler survey. And so points that are on this one-to-one line are points that our model is doing well at. And so you can see here that when we just use the deblazed spectra, we get a larger spread around these lines than when we use spectra that have been wavelet filtered. And so this is suggesting to us that the wavelet filtering removes a lot of systematics that aren't actually correlated to what happens physically in the star. So this was a success, and this is kind of more standard applications of these data-driven models that I'm talking about. So it was able to perform this label transfer, but next I'm going to kind of pivot and talk more about taking these data-driven models to the next level and actually trying to use them to look for binaries. So this is kind of pushing their limits into an application that's a little bit less standard. So if we have a spectral binary, this is, again, shown in the upper right panel, right? It's those overlapping features of the primary and the secondary star. Then in theory, if we fit it with our data-driven model, the data-driven model is not going to do well because it only knows how single stars behave. And that you're going to see large residuals, kind of like that yellow line, down at the bottom. So in other words, spectral binary should manifest as having sort of roughly 3%, 4% deviations from a single star that we might fit to the data, and we can use this to identify binaries. So if we find a spectrum that's not well described by our single star model, we can use that to say that it's potentially a binary. So that's what we did next. So I started with a couple different validation samples. I took single stars from a survey by Raghavan et al. In 2010 that looked for binaries among a nearby star population, found a lot of stars where there were no binaries. So we used those as our single star validation sample. And then we also had a catalog of binaries that Adam put together. A lot of these were published in his 2016 survey. And essentially, I fit my data-driven model to all the single stars and all the binaries, and I expected the single star model to do worse with the binaries because there's deviations from the secondary star that the single star model's not accounting for there. So what you'd expect to see in these graphs is that the green histogram should be sort of shifted to the right compared to the blue histograms. But as you are probably thinking to yourself, that's not what we're seeing here, and these histograms are overlapping quite a bit. So, and this is true for the Cannon data-driven model that I trained, and also the Payne data-driven model that I trained. So the kind of takeaway from this plot is that our model doesn't seem to be distinguishing between single stars and binaries in the way that we thought that it might. So here's what I think is going on. We predicted that the that the binary should deviate from the single star by about 3%. But what I'm finding is that our single star model isn't even really able to accurately predict the flux of the stars by more than 3%. So you can see here, I fit our data-driven models to a couple known single stars. And you can see in the residuals that the model's not doing a great job fitting to the data. And so if our model uncertainty is 3%, then we're not going to be able to detect these 3% fluctuations that the binary should possess. So we're limited by our performance of our data-driven models. We're starting to think about ideas why this might be happening. It's possible that high-res it's difficult to assemble homogeneous training data. There's also like Blaze function and point spread function instability in that instrument. If people in this room have trained data-driven models and maybe run into this before, I'd love for you to come talk to me because we're still trying to figure out why this isn't working. But not all hope is lost. So people have talked about these spectroscopic surveys that are coming out with more stable instrumentals. So there's a lot of hope to look for binaries there. And also fiber-fed spectrometers like KPF, which will have more stable point spread functions too. So I'm going to leave up my summary and take questions.
Okay, we have time for probably one question before coffee.
Hi, Isabel. This is super amazing. Great talk. Ida at CCA. So I'm really excited about this wavelet-based continuum normalization method. And I'm curious if you compared its performance to other kind of like commonly used normalization methods used for the Canon, like say Gaussian filtering, or I think Andy Casey used a version where he like kind of removed like combinations of like sine and cosine functions. So just curious how that compares to those. Second question is, if you have time, is like if you have tested to see how the wavelet-based continuum normalization compares for like performance to non-FGK dwarfs, like other stellar types, and how you think that might like change for these other different kinds of stars.
Wait, sorry, can you repeat like how the wavelet filtering behaves for which types of stars?
Oh yeah, just like curious about like whether it like behaves differently for like non-FGK dwarfs, like maybe red giants or M dwarfs, if you think it might like behave differently.
Yeah, those are really good questions. So the first thing that I would do next in this project is to compare the wavelet-based filtering to the more like standard continuum treatments that the Canon has used. So I would love to do that next. Haven't done that yet. And then in terms of the filtering on different spectral types, so right now I've trained these models on stars as cool as like 3,000 Kelvin, and I'm finding that it works pretty well for that, or seems to be limited more by like uncertainties in the cool star spectra themselves and things like that, but I haven't tried it yet on red giants. That would be really interesting.
All right, so we'll go ahead and thank Isabel one more time before David